ROM with the help of decoders and OR gates. Okay. In a similar way, what we'll see here, we'll see another kind of problem. So where in this problem, so we'll construct a higher ROMs with the help of the lower ROMs here. Like so, I want to construct 128 into 8 ROM with the help of 32 into 8 ROM here. Okay. So take down this problem. So take down this problem. So given a 32 to 8 ROM chip with an enable input, show the external connection necessary to construct 128 is to 8 ROM with 4 chips and a decoder. Four chips and a decoder. Okay, so there is a problem given in your exercise problem here. This is the exercise problem. So what we have to do here is we have to construct a 128 into 8 ROM here. Okay, so 128 into 8 ROM. So with the help of 32 into 8 ROM here. Okay, and a 2 to 4 decoder. Okay, so the construction will be like this. So coming to this, we'll talk about this 32 into 8 decoder, 32 into 8 ROM chip. So what happens when we use this 32 into 8 ROM chip? So how many number of what is size of decoder we have to use here? So here 8 is the number of outputs. Okay, so 8 is the number of outputs here. So this is the outputs. I mean we had to use 8 OR gates. Okay, so we had to use 8 OR gates. Okay, so this is output means we have to use 8 OR gates, and 32 can be written as 2 power 5 into 8 here. So this is k here. So the k is equal to 5. So k is equal to 5. So when k is equal to 5, so what is the size of decoder we had to use to construct this 32 into 8 ROM? So what is size of decoder?
5 into 32 decoder, sir.
5 into
2 power 5, sir.
2 power 5. So 5 into 2 power 5, 5 into k, that is k into 2 power k, that will be the size of decoder. So that is equal to 5 into 32. Decoder should be used to construct 132 into 8 ROM. So how many number of OR gates we require here? So 8 OR gates. So getting my point here.
Yes, sir.
Okay, so for one single 32 into 8 ROM, so we need 5 into 32 decoder and 8 OR gates, and the construction will be like this. So you know the construction, right? The construction is like this. 5 inputs here. So 1, 2, 3, 4, and 5. So these are the 5 inputs, and the inputs I'll name it as I0 to I5. So I0, this is I4, so I3, so I2, and I1. Okay, so this is the 5 inputs. Okay, and we'll be having 32, sorry, 0, 1, 2, 0, 1, 2, so up to 31. So total 32 outputs. So for a decoder, so this is 5 into 32. Okay, so we had to write all these things 1, 2, 3. Okay, and we have 8 outputs. 8 outputs. S1. So we need 8 OR gates here. So S1, S2 up to S8. So there, I mean, so we can write it as S naught, sorry, S naught to S7. What I can write here is S naught to S7. So this is S naught, this is S1, and similarly we'll be having up to S7 here. Okay, so this is normal 32 into 8, I mean 32 into 8 ROM here. So the normal structure of 32 into 8 ROM. So what we have to construct here is uh, we need 128 into 8 ROM here. So for that we need four these kind of structures here. Okay, so drawing all these things will make this I mean make the construction complex. So what I'll do, I'll draw a block diagram like this. Okay, so I'll draw a block diagram like this. The block diagram of 132 into 8 will be like this. So with inputs and outputs. So what are the inputs here? I naught to I4, outputs are S naught to S7. Okay, so that is what we'll draw here. So I told you like, so in this problem, so what we can see here is, so given a 32 into 8 ROM, so with the enable input here, so we'll be using enable input for each and every ROM here. So enable input is used for selection of that specific ROM here. So 4 and 5. Okay, so these are I naught to I4. So I naught, I1, I2, so I3, I4. Okay, this is 5 inputs, and instead of mentioning all the 32 decode outputs, what I'll do, I'll mention all the 8 outputs here. So inputs and outputs are essential here, and this is like 32, a single 32 into 8 ROM here. Okay, so I'll be having 8 outputs here, 3, 4, 5, 6, 7, 8. That is S naught to S7, S naught, S1, S2, S3 up to S7. Okay, this is a single 32 into 8 ROM. I told you like, so in the problem you can see with the enable input. So we'll be having an enable input here. So I'll put it as enable here. So this is enable. So which will enables uh, this one enables this specific ROM here. Okay, so what I need here, so I need 128 into 8 ROM. So this 128 into 8 ROM, so 32 into 4 gives 128 into 8 ROM. Okay, so I'll be using this four chips here. Okay, I'll be using this four ROM chips of this kind. So I'll use this architecture, and each of them will be selected with the help of this enable signal. So for this, I need 2 to 4 decoder. Okay, for this I need 2 to 4 decoder. So this 2 to 4 decoder selects one among the four 32 into 8 ROMs. So just like the previous cases, so what we had seen earlier, okay, so what we have seen earlier, so the previous cases are like, so with the help of so higher level multiplexers or decoders are constructed ఎలా చేస్తామో, so ఇది కూడా అలాగే. Okay, so we'll be using 432 into 8 ROM. This is 1, 2, 3, and 4. Okay, and so each one will be having four inputs here. So that is what I can give it as I naught to I4. So each one is having four inputs. I'll write as so four inputs and eight outputs. So each one is like 32 into 8. 32 into 8 ROM. So each one is 32 into 8 ROM here. Okay, and so each one will be having so four inputs. So four inputs can be written like this. So four inputs like I, I4, I3, I2, I1, I naught. So 4 inputs are given to, so all the 4 332 into, so 1 3 sorry 5, so 4 and 5. Okay, the 5 inputs are given to, so 32 into 8 ROM. Okay, so I am not using any decoders here. I'm not mentioning any decoders or OR gates here. Just the block diagram of this. Okay, and this, so each one will be having 5 inputs. So 1 2, I'm drawing only one here, so remaining all you draw. Okay, so 5 inputs. So similar case for the second one, third one, and fourth one also, and each one will be having enable input here. So this is E naught, so E1, E2, and E3. So this one will be given to a 2 to 4 decoder. So this is S naught, outputs are S naught, S1, S2 up to S7. Okay, you draw the diagram up to S naught to S7. Okay, and the enable input will be like this. So these enable inputs are given to a 2 to 4 decoder. So we'll be having a 2 to 4 decoder. So 4 outputs and 2 inputs. Like I4 is there, like, so here I'll write it as, so I5 and I6. And 4 outputs, each output is given to E naught. This is given to E naught. This is given to E1. And this is given to E2. And this is given to E3. Okay, so each one will be having S0 to S7. Okay, so S0 to S7. Okay, so this is the structure of the diagram. So getting my point here. So this will be the structure. Okay, and first of all, what we need here is, so 4 32 into 8 ROM here. So 32 into 8 can be, so the structure is given as a block diagram here. Okay, so the block diagram is like this. So this is a block diagram. So with mentioning the inputs and outputs, so 5 inputs and 8 outputs are mentioned with the help of a block diagram like this. So with a single enable output here, the enables are given to 2 to 4 decoder. So with the help of this decoder, with the decoder, only one 32 into 8 ROM can be activated. So at a time here. Okay, so only one 32 into 8 ROM can be activated here. Okay, so for example, if I take this like this, so if the values of I5 and I6, the values of I5 and I6 are equal to 1 0. Okay, so the values of I5, so I6 is equal to 1 0. So which ROM will be selected? So this is the first one, 0 1 2 3. So I'll name it as 0 1 2 and 3. So which one is selected when it is 1 0? So when I put the values of I5 I6 as I6 I5, so I6 I5 as 1 0. Okay, so which enable is activated here? So when it is 1 0, so which is activated? So which enable is activated here?
No.
Which one?
Even, sir.
1 0. When it is I6 I5 is equal to 1 0. So you have to always take from the largest numbers. Like if I say that I0 to I7 అంటే మీరు reverse this call, like I6 I7 I5, so the number should be counted like this. So I6 I5, so I4, so I3, I have to take the count like this. So in the decreasing order from left to right here. So I6 I5 is 1 0 ante. So the third, I mean, so 0 0 0 1, so 1 0. Okay, so 0 0 అయితే e node is activated. So 0 1 అయితే e1 is activated. So 1 0 అయితే e2 is activated. So e2 is activated. So e2 is activated ante this third, I mean, the 0 1 2. So this ROM will be activated here. Okay, this ROM will be activated. So getting my point here? Yes or no?
Sir.
Okay, so please follow, because when you are absent, like absent minded, and when you put your mobiles aside, so I can't help you, because this is the vast subject. I have to know each and every concept, and this is very important for you. Okay, so I have to understand, because the previous classes are very important to understand these concepts. So if you are absent for the previous classes, listen to those recordings. Okay, but you have to be prepared with the previous classes. I can't help you. I can't teach each and every time, teach with the previous concepts here. Okay, so third one is selected, and based on the values of I4 to I naught. Okay, so I4 to I naught, we'll select the remaining values. Okay, we'll select the remaining values. So like so I4 to I0. So if I say the I4 to I0 values as, so I4 is like 0. So I3 is 0 అనుకుందాము. So I2 is 1. So I1 is 0. I naught is 0. Okay, if I put I naught is 1 అనుకుందాం. If I put these values, what happens here out of 8 here? So what is the value I have to take here? So fifth line here. So fifth line should be activated here. Okay, so this is how we have to construct the ROMs here, higher ROMs with the help of the lower ROMs here. So if you are given this question, so you have to do like this. So you have to draw the block diagram of this one. Okay, so we have to not, you should not mention this decoders and OR gates here. So one single 32 into 8 ROM, so needs a 5 into 32 decoder here. So coming to the 128 into 8 ROM, 128 into 8 ROM. So 8 outputs are the same here. The 8 outputs are same, but the only thing is like, so 128. So 128 can be written as 2 power 7 here. So 2 power 7. So K is 7 here. So we need a 7 into 128 decoder. Okay, 7 into 128 decoders, where it needs 8 inputs. Sorry, 7 inputs. So here we got 0 1 2 3 4 5 inputs here, and here we'll get 2 inputs here. Total we'll get a 7 inputs here. Okay, so 7 into 128 decoders are needed to construct the, so 128 into 8 ROM here. Clear?
Yes, sir.
Right?
Sir.
Yeah, so this is the kind of problems you may get. So ROM is also called as PROM, so programmable ROM. So I'll explain the kinds of ROMs here. Okay, so meanwhile the construction of ROM will be like this. The construction of ROMs will be like this, like 128 ROMs, or with the help of other ROMs will be like, you'll get this kind of problems also. Clear? Yeah, we'll move to the kinds
Yes,
of
sir.
ROM. Right, so we'll check the kind of ROMs here. Okay, yeah, only memory. Yeah, coming to the types of ROMs here. Okay, so generally, so ROM, so what do you remember when you see a ROM here? So it is, we can perform only read operation. Okay, so wait a minute. Right. Yeah, if this is the kind of problem you will get here. So this cross joins, like, so this will be depending, like, so I'll put a cross mark here. I'll put a cross mark like this based on the truth table. So this is a truth table, for example. So example truth table. So this is not a kind of truth table here. So I'll put a cross marks here. So based on the truth table here. Okay, so I'll program them based on the truth table. Okay, I'll connect them based on the truth tables here. Okay, so this is called as programming here. So selecting the truth table here, and based on the truth tables I'll put a cross marks, so wherever there is a 1, so I'll not put a cross mark wherever there is not a 0. Okay, so cross mark for your understanding, but in case of the programming part, so hardware part, so this is the case that will happen here. Okay, so the required parts in the ROM may be programmed in 4 different ways. So the meaning of programming is like, so how to put a cross marks there. So the first one what we did is like, with the help of truth tables we are putting a cross marks there. Okay, so the programming can be done in 4 ways here. Okay, the programming can be done in 4 ways. The first one is called as mask programming. So understand this concept here. So we'll explain the types of ROM based on this. The first one is called as the mask programming. Okay, so what will be done here is, so you'll give a truth table, the designer. So designer means if I'm designing any circuit, so I told you like a 4-bit number which generates a square. Okay, so I'll be giving the truth table to the manufacturer there. So what the semiconductor company will do, so he'll do the programming based on your truth table. Okay, so so the manufacturer makes the corresponding mask for the parts to produce ones and zeros according to the customer's truth table here. Okay, so when you have the truth table here, so the programmer will do the fabrication. He'll establish the connection whenever there is a 1, and he'll not establish the connection whenever there is a 0. Okay, so the semiconductor industry will be like this, like he'll be having a semiconductor, they will be having some decoders and or gates there. Okay, and the connections between decoders and or gates will be given, so whenever there is 1 in the truth table. Okay, that programming part, so I mean the programming here refers to the hardware. Okay, so the connection is established, so whenever we have a 1 in the truth table, and whenever there is 0, so there is no connection between the or gates and the decoders here. Okay, so this is called as mask programming here. So this is the procedure for fabricating a ROM requires, I mean we needed truth tables here. Okay, and truth tables is submitted to the manufacturer here, and what the manufacturer will do here is, so it will produce a path whenever there is a 1, so he'll produce a connection. He'll have a connection, he'll generate a connection, or he'll generate a connection whenever there is a 1. Okay, and for 0 there is no connection there. Okay, and this is very costlier one, because so he'll give a single truth table and he'll say that, so I need a single circuit. So when you want a single circuit, implementation of a single truth table for a single circuit is very costly. Okay, suppose if you say that, so I need a truth table for some thousand of ROMs here, the same devices, I need a same devices here, so then it will be economical. Okay, so the mask programming is economical, so only if the large quantities of same ROM configuration is ordered here. Okay, so when we order the same configuration, so we'll get the I mean the cost of the circuits may be decreased here. Okay, so whenever we talk about the semiconductor industry or any kind of architectures, we always talk about the cost here, or we always talk about the area occupied, or we always talk about the optimization in the sense, I want to reduce the power. Okay, or I want to reduce the size of the circuits, I want to reduce the size of the hardware, I want to increase the speed of the circuit. So increasing ante speed vastundi, so reducing ante, so all these factors will come, reduce the area, reduce the power. Okay, reducing the heat here. Okay, so we'll get all these things here. Okay, so we'll get all these things when we come across the circuits here. Okay, so when we come across this, so this is the case here. So the first kind of programming is mask programming, where the designer, he or she will be giving the truth table to the manufacturer here. The manufacturer will manufacture the ROM, will give the connections when there is a 1, and he'll leave when there is a 0 there. Okay, so this is economical when it is produced in the large quantities. Okay, so for small quantities it is more economical to use the second type of ROM here, so called as programmable read-only memory, which is called as PROM. So sometimes ROM is called as PROM here, so it's fine, like ROM is also taken with the name of PROM here. Okay, so what happens here is, so he establishes a connection. So you can see here, so 1 minute. Okay, so earlier what it will be done here is, so the manufacturer, in case of the PROM, so we'll put all cross marks here. So I mean fuses will be generated. I mean there'll be fuses for all the things here. Okay, so here, I mean, initially there are all ones. I mean, initially there'll be all contacts. Okay, from the decoder to the OR gates. So getting my point here.
Yeah, sir.
Yeah, initially there'll be all ones here. So all ones. So there'll be fuses in the cross sections here. So there'll be cross sections here. So there'll be fuses in each and every cross section here. Okay, so that will be given to the designer here. What the designer will do? So the designer will blow the fuses whenever there is no need of there is no need of connection between the decoder to the OR gates here. Okay, so initially they are all highs here. So initially they are fuses intact here. The meaning of fuses is just like your electrical fuses here also will be having the fuses here. The fuses will be blown when there is a zero. So the fuses will be intact when there is a one. Clear? Okay, so we'll have fuses in all the intersections here. So here we'll get a 256 intersections. There'll be fuses in all the intersections. The meaning of fuses is like, so there'll be all ones in the 256 intersections here. Okay, that will be given to the programmer. So with the help of some tools here, so what we'll do here is, so we'll with the help of the truth table. So what is the truth table we got here? So what we'll do here is, so we'll blow the fuses whenever there is a zero, and we'll keep the fuses as it is intact. Okay, so whenever there is a one. Okay, so you can check here the PROM. Okay, so the PROM, when ordered, the PROM units contains all the fuses intact, giving all the ones in the bits of the stored words. Okay, the fuses in the PROMs are blown by the application of high voltage pulse. Okay, to the device to a special pin. Okay, and a blown fuse defines a binary zero state, and intact fuse defines a binary one state. Okay, so whenever if I blow the fuse here, so it will be a zero. Okay, if I don't blow the fuse, it will be a binary one state here. Okay, and this procedure allows the user to enter, to program the PROM in the laboratory to achieve the desired relation between the input address and the stored words here. We have to get the relationship right, so we have to implement the truth table of our choice with the help of this circuits here. So what we have to do? So we have to take a truth table, and based on the truth table only, we have to design the circuits here. Okay, and so we will be having some special instruments for the PROM programmers, so which are used to facilitate these procedures here. Okay, so there is a second kind, that is a PROM here. So the first one is mask programming, so where the manufacturer will be doing the implementation of the truth table of our truth table, okay, in the laboratories in the semiconductor company. Okay, and the second one is PROM here. So here all the fuses are intact here. So whenever I need a zero, I'll blow the fuse. So that is the second one, that is PROM here. Okay, so even though I'll call it as a programmable here, so these are the hardware procedures. Okay, so these are the hardware procedures. I'm not writing any program here, just performing the blowing of fuses or keeping them intact. So we are performing them in a specific manner. So that is why it is called as a programming here. Okay, so the meaning of this is, like I'm using this a specific pattern here. So what is that pattern? Your truth table. Okay, so your truth table is a pattern. So this truth table is implemented in a hardware manner on your PROM here. So that's why it is called as a programming here. Okay, so there's a hardware procedure. So what are the procedures we are using? So these are the hardware procedures here. Getting my point here?
Yes, sir.
Yes, sir.
Okay. And next, so there'll be like, so whenever what we do with the PROM, so it is permanent. So when it is once it is programmed, so we can't change it. Okay, so I have to remember this. So if I blow the fuses, so I can't make it as one again here. Okay, so once it is done with the initial application, so once we are done with the implementation of truth table, I can't use it for the other application. I can't use them for the another application. So that is a drawback of PROM here. Okay, that is a drawback of the PROM. So that can be overcome with the help of two kinds of ROMs here, so which is called as EPROM and E square PROM here. Okay, so what is the disadvantage here? So once it is, once we implement the truth table on PROM, so what happens there here is, so PROM, so what it will do, so when the PROM, so once we implement the truth table, so we can't use it for the another application. So that is a disadvantage. So we can't erase the what are the things we program there. But in case of electrically erasable, for in case of EPROM, so which is called as erasable PROM here, which is called as erasable PROM. So we'll have some initial state. Okay, we'll have some initial state. So the meaning of initial state, what I can say. So what happens when we restart your mobile? So what happens when we restart your mobile?
All programs will stop.
So I mean, it will come to the initial state. So when you restart your computer, so every time, so when you restart your mobile or restart your computer, so it will come to the initial state. I mean, from there, you'll start your all the programs and all the apps will be open from that state only, right?
Yes, sir.
So whatever the programs we have, whatever the whatever the apps you have, you'll open only after the initial state only after the initial state. So in the same way, so this erasable PROM, so we'll have some initial state here, okay, and afterwards initial state. So what I'll do, I'll program something, okay, I'll take a truth table and program something, okay, it will come to some other state, okay, after using that. PROM for some other application. So what I had to do here is I'll erase this and take back this EEPROM to the initial state. I'll erase this and take back the EEPROM to the initial state. So how the erasing will be done here? So this erasing will be done with the help of special ultraviolet light here. Okay, this EEPROM is placed under special ultraviolet ray light for given length of time. Okay, and the short wave radiation discharges the internal floating gates that serve as the program connections. After erasure, the EEPROM returns to the initial state and give reprogram to the new set of values. So that is what I'm saying. So when you restart your mobile, so all the earlier versions of all the earlier apps, what you have programmed and what you have opened will be erased and it will come to the initial states. In the same way, this erasable PROM, so we'll have some initial state. From the initial state, we'll program something. We'll implement a truth table on that EEPROM here. Okay. After implementing, what it will do here is will erase them. So how the erasing procedure is done, this is important. So we'll place this PROM under the UV light, so under a special ultraviolet light, so for some amount of time. So that ultraviolet light erases the whatever the programming things that are done on the PROM here, okay, and makes this PROM to come to the initial state here. I mean, we'll get back this PROM to the initial state. So from there, we can implement another kind of truth table on this PROM here. So getting my point here.
Yes, sir.
Okay. So this is EEPROM. So electrically, erasable PROM. So where the erasing is done, where the PROM is done, I mean, will be taken back to the initial state with the help of the ultraviolet rays here, ultraviolet light. Okay. And coming to the next kind of PROM here, so which is electrically erasable PROM, that is called as E square PROM here. So where earlier case we are used the UV light here, but here what we'll do, so here what we'll do, we'll erase the with the help of electrical signals. Okay, so the connections can be erased with the help of some electrical signals instead of the ultraviolet light here. Okay, so with the help of the ultraviolet light. So earlier case is like, so this PROM should be removed and it should be taken into ultraviolet light here. But here in this case, putting this PROM into the electrical socket only, so we can erase this previous connections here. Getting my point here? Okay. Yeah, so electrically erasable PROM is nothing but, so we can erase them with the help of some electrical signals. So that is the major difference here. So previously programmed connections can be erased with the help of the electrical signals instead of the ultraviolet rays here. Okay, so that is the advantage of this E square PROM here. Okay, and the new kind of PROMs will be like flash memory devices. Okay, so this is similar to E square PROM only. Okay, but the advantage of this flash memory compared to the previous versions is, so earlier we have to erase all the programmed bit patterns here. So whatever the connections we have done, so we have to erase them and we have to bring them to the initial state here. Whereas in case of flash memory devices, we can erase a part of the connections here. Okay, we can erase, we can selectively erase the programs here. I mean, we can selectively erase the connections here. For example, I'll be having 8 entries in the truth tables, like 000 to 111. So I want to erase only up to 100. Okay, so I'll erase only this part of the truth table, the connections representing this part of the truth table. So I want to erase the connections only specific to this part of the truth table. So then I'll prefer this flash memory devices. Okay, it has some additional circuitry to selectively program and erase the device in the circuit. So we can program a specific part of the circuit, or we can erase the specific part of the circuit. Clear?
Yes, sir.
Okay, so that is the advantage of this flash memory devices here. So this is the kinds of ROM we'll be using here. Okay, the kinds of ROM are nothing but so mask programming ROM here. So the mask programming is where the programming will be done by the manufacturer itself, and we'll be having a PROM, so which is programmable read-only memory, where the designer will be given the circuit with all the fuses intact. So whenever there is a zero, the fuses will be blown here. So that is PROM here, where the disadvantage of this is we can't bring back the, I mean, we can use this PROM only for a single usage here. Okay, so we can use them only for single use here. Whereas in case of other kinds of ROM here, so we'll be having some EPROM and E square PROM. So where the data will be erased, I mean, the programming will be done or the connections will be erased with the help of some special ultraviolet UV rays. So in case of EPROM, in case of E square PROM, so the connections will be erased with the help of some electrical signals. So that is the thing here. On flash memory devices, the programming or erasing will be done for a specific part of the circuit. So that is the advantage of the flash memory devices here. Okay, and this PROM is also called as programmable logic device here. Okay, so PROM is also called as the programmable logic device, and we have the kinds of PROMs here. Okay, we'll be having some kinds of PROM. So whenever you are given the problem like ROMs and ichna, like unte PROMs and ichna kuda, so it is a ROM. Okay, so understand that. So whenever it is given like PROM or ROM, it is the same here. Okay, and next we'll be having some combinational PLDs. Okay, the PROM is a combinational program logic device. So what I said is like, so the PLD is a combinational, I mean, it is called as programmable logic device. Okay, and we'll be having some three kinds of PLDs here. Okay, we'll be having three kinds of PLDs here. Okay, so take down this three kinds here. The PROM is a combinational programmable logic device. Okay, an integrated circuit with programmable gates divided into AND array and OR array. Okay, so we'll be having some AND arrays and OR arrays. So decoder is nothing but an AND array. Okay, you can see. So whenever I want to implement any circuits, I need a decoder. I'm using some decoder and OR gates, right? So decoder OR gate uses what is the meaning of that? So decoder is construction is done with the help of AND gates only, series of AND gates. Yes or no?
Yeah,
So
sir.
so you can check the structure of decoder when go to the decoder topic. So when I'm constructing the decoder, so you can check that. So decoder consists of AND gates here. So and we are using OR gates to the output here. So this PROMs or programmable logic devices will have some AND array and OR array. Array means a set of AND gates. OR array means a set of OR gates. Okay. So this is AND array and OR array. So or fixed. I mean, we'll be having some set of AND array and set of OR array in case of the PLDs here. In case of the PLD. So PROM is also called as a PLD. Okay. So PROM is a combinational PLD, and based on this arrangement of this AND array and OR array, so we can divide this PLDs into three kinds here. I'm getting my point here. So okay. So whatever the ROM we are using, it is called as PROM we are using, it is called as combinational programmable logic devices, PLDs here, and these PLDs are of three kinds here, and the PLD will have some AND array and OR array. Okay, so based on the AND array and OR array arrangement, the PLDs are divided here. Okay, the PLDs are divided. Okay, so we'll be having some PLDs here. Okay, so these are the three kinds here. Okay, the first one is PROM, we know this. Okay, the first one is PROM. So where we'll be having a fixed AND array. So remember this, these are important. Okay, so PLDs are divided into three. So the first kind is like PROM. So programmable read-only memory, it has fixed and array. So what we discussed earlier. Okay, so fixed and array. So if I told you like to construct 32 into 8 ROM here. So what we have done, we used 5 into 32 decoder. Yes or no?
Yes, sir.
Yes, sir.
Okay, so 5 into 32 decoder, it is fixed. So we will not change it. We will not reduce the number of gates or reduce the size of the decoder. So we will not change it. So we'll be having fixed and array. So 32 outputs. So we'll be using 32 AND gates there. For a decoder, we'll be using 32 AND gates. Yes or no? So for
Yeah, sir.
32 into 8, we'll be using 32 AND gates, right? Okay, so that is fixed here. Okay, but in case of OR array, so OR array can be programmable here. OR array can be programmable. So the meaning of programmable here is I can reduce them or I can increase them. So most probably reducing only. Okay, so see the example earlier. So four squares, we have seen the 4-bit square and the example you said. So check that example. Okay, so actually the 8 OR gates used here, but I used only 6. Yes or no?
Yes, sir.
Okay, because so that can be programmed, because one of the outputs is 0 and one of the outputs is equal to one of the inputs. So I eliminated 2 OR gates there. So that is programmable. So programmable in the sense we can change the functionality of that array here. Okay, so we can reduce the number of OR gates that are going to be used here. So that is the meaning of programming here. Yes or no? So getting my point here. So PLDs here. So we are talking about PLDs, programmable logical devices. A PLD is nothing but it will be having some AND array and OR array. So these AND arrays can be fixed or programmed. Okay, or OR arrays can be fixed or programmable here. So fixed in the sense we'll use only a specific number of AND gates and will not change the number of AND gates used. Okay, so programmable means so we can change we can reduce the number of OR gates and AND gates used there. So based on our application or based on our problem, we can use the number of OR gates which are only needed for this circuit here, which are only needed for the circuit. So that is the meaning of programming, right? So whenever I say that, so write a program for addition of 2 numbers and done. So what you will do? Say in a C language, what you will do? You'll write a program for only addition of 2 numbers only. Yes or no?
Yes, sir.
Okay, so you'll not write a program for all the arithmetic operations. Ante kada?
Yeah, sir.
Okay, so so this is the kind here. So if I say that what is the function of ALU? So if I say that write a program for ALU. So ALU will have all the arithmetic operations, logical operations, and all those things. So it is a general format there. So it is fixed here. So ALU has some fixed functions. Okay, whereas I want to take a specific function of ALU, so I'll program that. I mean, I'll write the program for only that specific part of the thing we needed there. So ALU means we can write anything, right? So we can use addition, subtraction, multiplication, different kinds of operations. Okay, so this is fixed part here. Another one is programmable part. So programmable part depends upon our requirement. Depends. I mean, it is our requirement. So we'll program our requirement and we'll we will design the circuits based on our requirement or our truth table. So that is the meaning of programmable here. Clear?
Yes, sir.
Okay, so there's the first part here, first kind of PLD here, that is PROM. Okay, and second kind of PLD is like PAL, which is called as a programmable array logic. So in case of programmable array logic, so we'll be having programmable and array. Okay, so programmable and array and a fixed OR array. So number of OR gates is fixed in case of PALs here. Okay, number of OR gates are fixed here in case of the PALs here. Okay, and we'll be having programmable AND array. So the AND gates, usage of AND gates will be deferred here. So based on our requirement or based on our truth table. Okay, so that is PAL here. And the last kind is like PLA. So where both are programmable here. So we'll be having programmable AND array and programmable OR array here. So that is PLA here. Clear? So these are the 3 kinds of PLDs here. Okay, so PLA is nothing but, so it is a programmable logic device with programmable AND array and programmable OR array. Okay.
Yes, sir.
Okay, so that is the concept here. So now we'll see the concept of PLA here. So we'll directly go straight away go with the problems here. So how the PLAs will be. Okay, so the PLA problems will be given. So PLAs are mostly used here. Okay, so we'll be having some programmable AND array and programmable OR array. So generally in a fixed AND array we have to use all the minterms, right? So 0 to 32 all the minterms are used. Okay, and we'll program the OR array only. Whereas in case of PLA here, so we can use the customized AND array and we can use the customized OR array. I mean, we can use them whichever are essential. So we'll not use all of them here. Okay, we can reduce the number of OR gates also. We can reduce the number of OR gates. We can reduce the number of AND gates based on our requirement here. Okay.
Okay, sir.
Got the point here. So this is the concept of PLDs here. Okay. So we'll study about this PAL right now. So PLA right now. Okay. So already we are done with this PROMs. So whatever we discussed in the last classes is about PROMs here. And next we'll start this PLA. The problems will be interesting here. Okay. So PLA will study about this PLA and we'll see the kinds of problems related to this PLA here. Yeah. So shall I proceed?
Yeah, sir.
Yeah. So class will be for another 40 minutes. Okay. So I had to be here because I had to fasten up the things by the end of this month. So we had to finish this syllabus and I'll get all the recordings. So what I'll do, so I'll have the earlier recordings of this circuits of like flip flops and all those things. I had taught earlier. I taught for this triple E people. I have the recordings of at least 30 classes. Okay, so what I'll do, I'll be sharing those recordings if possible. And meanwhile, if I finish this unit, so what you have to do here is you be prepared with the videos. Okay, so after your preparation, after your basic understanding, I'll start the classes. Okay, so you do the things parallelly. Okay, so what you have to do here is you do the things parallelly and you understand the basic concepts there, and afterwards I'll be taking the class because flip flops will take lots and lots of hours. Okay, so I want you to prepare in advance. Okay, so after your basic preparation, I can start the class here so that your understanding will be easy and my task will be very easy. Clear?
Okay, sir.
Okay, yeah. The concept is like programmable logic array. Okay. So what I'll do, I'll start with the basic things here. So how to construct a PLA. So afterwards, I'll go with the problem. Okay. So the main thing here is I have to draw the diagram, circuit diagram, and afterwards, the main things like I have to draw a PLA programmable table here. Okay. So I need a PLA programming table. Okay. And afterwards, I need to draw the diagram here. Okay. I need to derive the equations. I need to draw the diagram. Yeah. So
Yeah, sir.
taking the problem straight away. So implement the following three Boolean functions with PLA. Okay. So take down this f1 of a comma b comma c is equal to sigma of 0, 1 to 4 f2 of a comma b comma c is equal to, so sigma, you write the symbol, sigma of 0, 5, 6, 7 and f3 of abc is equal to sigma of 0,357 0, 3, 5, 7. So draw the Kmax for this. So find the equation for F1, F2, F3. Okay, so there is a condition here, so I'll let you know. So what is the condition here? So first of all, find the equations for F1, F2, and F3. Find the equations for F1, F2, F3. Okay, yeah. Right. So this f of ABC, right? So this is A and this is BC. This is 0, 0, 0, 1. So 1, 0. Sorry, 1, 1, 1, 0, and this is 0, 1. And first of all, we have to find F1. Okay, so we have to find F1 here. Okay, so F1 of ABC is 0, 1, 2, 4. So this is 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 4. This is 0, this is 1, this is 2, and this is 4. Okay, so this is 1, 1, 0, 1, 2, 4, right? This is F1. Yes or no?
Yes, sir.
Give me the value of F1. Tell me the value of F1. So this is one pair here. This is another pair, and this is another pair. So we'll be having 3 pairs here. Okay. So what are the values of these three pairs here? So this one. So this one is like B bar, C bar. Okay. And these two will be like so A bar. So A bar, and this two, the combination of these two will give C bar. So sorry, A bar, B bar.
B bar.
Yeah, A bar, B bar, and this two, last two. So this is A bar. Okay, so A bar into and the last two C bar. Yeah, A bar, C. Okay, so this is F1. Okay, so I'll let you know here. So we have to find two methods here. So this is true form here. This is called as true form. When we group the ones, it is called as a true form. Okay, so this is the true form. So understand this. So this is the true form here. So getting my point here.
Yes, sir.
So we'll be having true form. In case of PA list, we have to find two forms here. Two form. One is true form. Other one is the complement form. Okay, I want to find F1 and F1 bar. Other one is F1 bar. So how can we find F1 bar? So how can you find F1 bar? With the help of the truth table. I mean, F1 of ABC is equal to sigma of 0, 1, 2, 4. If I want F complement, so what I have to do?
Remaining, sir.
The remaining number.
Remaining numbers are zeros generally. Remaining numbers are treated as zeros here. Okay, so those numbers should be grouped here. Okay, those numbers should be grouped. So getting my point here. Okay, so I have to find two methods here. So one is true form and complement form, each and every thing only with PLAs here. So only with PLAs I have to find the true form and the complement form. I'll let you know so why we are using a true form or complement form. Okay, so 0 1 2 4. So remaining numbers, so like this number, so this one, so this one and this one, so these are all zeros here. Okay, so this is 0, this is 0 and this is 0 and this is 0. So find the grouping here. So grouping, so this is 0 0 0 1, so 1 0 1 1, there is 0 and 1. Okay, so we can group this two. Okay, so what is this value? BC. Okay, plus we can group this two. So what is this value? This is A into
A B bar.
A B bar. So
A C,
this,
sir.
yeah, AC.
C, sir.
Yeah, this two
A B, sir.
AB. Okay, so F1 bar is equal to BC plus AC plus AB whole bar. Okay, BC plus AC plus AB whole bar. Okay, so whenever you are selecting a circuit, so you have to check whether that it will be having less number of product terms. Okay, so I have to compare this one. Like you have to compare uh, F1 with F2 and F3. Okay, so I have to take true forms and the complement forms. Okay, so I have to select these values of F1 and select చేసుకోవచ్చు, F1 bar and select చేసుకోవచ్చు ఇక్కడ, లేకుంటే F2 and select చేసుకోవచ్చు, F2 bar and select చేసుకోవచ్చు, but you have to select only one of them. Okay, we have to select only one of them. We have to select F1 or F1 bar, F2 or F2 or F2 bar, and F3 or F3 bar in such a way that so there is some common terms in between which are shared between F1 bar or F2 F2 bar and F3 F3 bar. Getting my point here?
Yes, sir.
ఓకే, సో మీరు F1 F2 F3 సెలెక్ట్ చేసుకున్నప్పుడు ఎలా ఉండాలి అంటే ట్రూ ఫార్మ్స్ కాంప్లిమెంట్ ఫార్మ్స్ తీసుకుంటారు. ఆ ట్రూ ఫార్మ్స్ కాంప్లిమెంట్ ఫార్మ్స్ కూడా ఎలా సెలెక్ట్ చేసుకోవాలి అంటే సో ఆ టర్మ్స్ ఏవైతే ఉన్నాయో వేరే దాంట్లో రిపీట్ అయితే దాన్ని సెలెక్ట్ చేసుకోవాలి. ఓకే, ఫర్ ఎగ్జాంపుల్ ఇప్పుడు F1 బార్ తీసుకుంటాను కదా, F1 బార్ లో ఉన్న టర్మ్స్ లేదా F2 లో కానీ లేకుంటే F2 బార్ లో కానీ F3 లో కానీ F3 బార్ లో కానీ రిపీట్ అయినాయి అనుకోండి, సో వీ హావ్ టు రెడ్యూస్ ద నంబర్ ఆఫ్ ప్రోడక్ట్ టర్మ్స్ హియర్. Okay, we have to reduce the number of the product terms. So we will select the two or complement forms in such a way that it will reduce the number of product terms here. The meaning of this is so the repetitive product terms, the functions which will give the repetitive product terms are selected here. Okay, yes or no?
Yes, sir.
Okay, so meanwhile, you remember this. So we'll find F1 F1 bar, F2 F2 bar, and F3 F3 bar. So in the last we'll decide so which we have to use here, whether we have to use the complement term, whether we have to use the true term here. So true term use cheyala, complement term use cheyala, last we decide cheddam. Okay.
Okay, sir.
Okay. Yeah. So next, go with this F2. So F2 is 0 5 6 7. So these are the F1 F2 terms, and F2 is like okay 0 5 6 7. So what is 0 5 6 7? This is 0 and 0 1 2 3 2 3 4 5 6 7. Okay, and the remaining terms are the complement terms here. Okay, so tell me these values F2 and F2 bar.
AB plus AC plus A bar B bar, sir.
AB plus AC plus A bar B
A
bar.
bar B bar C bar. A bar B bar.
Yeah, write the F2 and F2 bar, and the similar way F3 and F3 bar. right? So this is circuit here. So this two and this two and this one. Okay, and here this two, this two, and this one. So this is F2 bar and this is F2. So F2 is like this is 0 1 0 0 0 1, so 1 0 1 1. Okay, so this is A bar B bar C bar plus these two values. It is like A. So what is this value? So what is that value here? So A and these two combinations are taken here. So it is AC and this is
AB. AB plus
AB.
AC.
AB.
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 Okay, and F2 bar. So what is it?
ABC
So ABC
plus A bar C bar
plus A bar C bar plus
A bar B bar.
plus A bar. Okay, this is F2 and F2 bar. Next, coming to this F3. So understand this concept. So we'll solve 3 or 4 problems. So we'll get some clarity there. So 0 1 0 0 0 0. Sorry, 0 0 0 1. So 0 1 1. So K maps you have to be perfect. So with K maps we can solve most of the problems here. So 0 3 5 7. So sigma of 0 3 5 7. It's 0 and this 3 and this is 5 and this is 7. Okay, and remaining terms, sorry, this is 0, this is 0, this is 0 and this is 0. Tell me the outputs of this.
AC
So F3 is like AC,
by 1.
so plus BC. So this is,
BC.
yeah, BC. Correct, yeah, this is AC, BC plus A bar, B bar.
C bar.
Okay, and what is the other term here? So this 2 is like F3 bar, F3 complement is equal to this 2 is like it will give,
A bar C bar.
yeah. So sorry, so B C bar. Okay, so and so any other combinations possible here? So this one and this one, yeah, this one and this one. So what is this one and this one? So it is A value and these two combinations will give C bar. So A C bar, right? Yes or no?
Yes, sir.
Okay, and this value. So what is this value
Yes,
here?
sir.
This value is A bar, B bar.
A bar, B bar, C.
Okay, so this is true form and this is the complement form. I'll name it as tree T here and this is the complement form here. Okay, so this is the true form, this is the complement form. This is T and this is C, and this is T and this is C here. Okay, so now what I have to do here is, so which one I have to select here? So which true combinations I have to make it to the final thing here? So which complement term I have to take it to the final term here? Okay, so selection is based on the observation. Okay, so check the value of F1 true complement and F1 bar చూడండి ఒకసారి. So F1 bar చూడండి, like true forms and complement forms చూడండి. So BC bar A bar B bar plus A bar C bar. Okay, so ఎక్కడెక్కడ ఉన్నాయి చూడండి ఒకసారి. సో ఇది ఉందా, ఇది ఉందా? సో F1 లో ఉన్న టర్మ్స్ ఉన్నాయా ఎక్కువ, F1 బార్ లో ఉన్న టర్మ్స్ ఎక్కువ ఉన్నాయా? So because my writing is like it's not clear here. Okay, so I'll take this one. I think we have the example of this. I don't know. Yeah, so we have this example. Wait a minute. I think in this textbook it's not mentioned. So another example is given. So in my textbook, another example is given. So no problem. So you tell me, okay. So this is example, right? So this is F1 and F1 bar, and this is F2 and F2 bar. Okay. So you can check here. This F1 values BC plus AC plus AB. Okay. We have AC here. We have AB here. Okay. And I think I have BC here. I have AC here. Okay. So you can check here. So B bar, C bar. So where we can find B bar, C bar? So there is no B bar, C bar. So choose Naragada. Okay. So check the product terms here. So B bar, C bar is not there in F2 or F2 bar. So true form lo ledu, complement form lo ledu. Okay. And B bar, C bar is not in true form on the complement form of F3. So we have BC bar, but we don't have B bar, C bar. And we have A bar, B bar. So check the values of A bar, B bar. So A bar, B bar is not in true form and complement form of F2. And A bar, B bar is not in true form and complement form of F3 here. And A bar, C bar. So A bar, C bar, we have only once in F2 bar here. Okay. But not in F3. F3 true forms and the complement form. Whereas take the second one, we have BC plus AC plus AB. Okay, we have AC plus AB in F2 here. Okay, so F2 lo AC plus AB undi. Okay, and we have AC plus BC in F3. Yes or no?
Sir, F2 bar tappu రాస్
ఏం రాసినమ్మా F2 బార్ ఏమొచ్చింది?
A B bar C bar plus A bar C plus A bar B whole bar.
A B bar, yeah. So A B bar C bar, A B bar C bar plus
A
this
bar
two
C, sir.
A bar C naadi. Yeah, A bar C, and this is A bar B na. So 1 1 and so 1 0. So we'll have B here. So A bar B. So this is correct, right? Yeah, it's correct only. Like this is A bar and the combination of these two. So we'll give the value of B here. So this is B bar C plus B, sorry, BC plus BC bar. So C bar has common, B has common here. C plus C bar is equal to 1. It's B and it's A bar here. Okay. So you check these values here. The values of F1 bar are repeated in F2. Okay. So we have AC plus AB is in F2 here. Okay. And we have AC plus BC. So that is AC plus BC in F3. Okay. So what I'll prefer here is I'll prefer F1 bar, F2 and F3 in the final output here. Okay. I'll prefer the complement term of F1 here. I'll prefer the true forms of F2 and true form of F3. Yes or no? No response. So do you understand or not?
Yes, sir.
Only one.
Yes, sir.
So please understand this, because you find the true forms and the complement forms. So this requires a minimum. I mean, మీరు అది ఒకవేళ నేను కాంప్లిమెంట్ ఫామ్ తీసుకుంటా దీంట్లో అంటే వస్తుంది, సర్క్యూట్ ఏం వస్తుంది, బట్ ద కాంప్లెక్సిటీ కొంచెం పెరుగుతుంది అంతే. అక్కడ మిస్టేక్ అని చెప్పాను కానీ, బట్ యూ నీడ్ a little bit of common sense here. So our main aim is to reduce the number of product terms here. Okay, so take the combination in such a way that so the combination is reducing the number of product terms here. Clear?
Yes, sir.
Where are other people? All people are mute. Select all names and you turn on your videos. So I'll see your faces. I'll know what you're doing. So who told you to drop this attendance? Balaji unnada? So you should be very patient. This subject cannot be learned in 1 hour, or I can't complete the class within 1 hour. You have to bear with me. Right. So what are the case? So you understand or not? So we'll see. I mean, next class I'll talk to you people like. So we'll see. So true forms and complement forms. So we'll take the complement form of F1. So we'll take the complement form, and F2 will take the true form, and F3 will take the again the true form here. Okay. So the next step is what we have to do. First of all, when you are given the Boolean functions here. Okay, so when you are given the functions here, so what we have to do here is we have to take the true forms and the complement forms. Okay, and afterwards finalize the things which are to be included here. So I included the F1 complement, F2 true forms, and F3 true forms here. Okay, I have to draw a PLA programming table, so which is very important part here. Okay, the PLA programming table. So next step is PLA programming table. Okay. So the PLA programming table. So first of all, what we have to do, we have to mention all the product terms available here. Okay. So the PLA programming table will be like this. Okay. So product terms, number of product terms, inputs. Okay. So what are the product terms here? So what in case of F1? So what are the product terms we used here? So AB is a product term. So the first product term, AC, and the last one is BC. Okay. So there's a first product term here. Okay, so that is in case of F1, which is a complement form we are taken here. Okay, and coming to F2, what is the value? We have selected the true form here. So true form in the sense, so I'll write the equations. Why to get confused? So F1 is equal to, we got these values here. So I mean, we are taking complement form. So what we'll do here is we'll put a complement mark there. So AB plus AC plus, so BC whole bar. So that is meaning of complement form here, and is equal to AB plus AC. Sorry. So F2 is equal to AB plus AC plus A bar, B bar, C bar, and F3 is equal to BC plus AC plus A bar, B bar, C bar. So this is the values we got here. So this is the complement form, and the other one is the true forms here. Now I have to mention the product terms here. Okay, in a programming table, the first term is like product terms. We have to mention the product terms here. Okay, so AB plus AC plus BC in the first one. Next, the repetitions are done here. So AB is there, AC is there. There is no way to mention that, and we have A bar, B bar, and C bar. So A bar, B bar, and C bar. Okay, and we have F3. We have all these things covered in the F1 and F2. So there is no way to mention the remaining terms here. We have 4 product terms here. Name number it as 1. So take down this table. 2, 3, and 4. Okay, and so what we have to do here is, so what are the inputs available here? So this is the first step here. So identifying the product terms from the true forms and the complement forms. So you can compare also, like if you take any different combinations of true forms and the complement forms, you can compare. So compare like how many product terms we are getting here. Okay, so if I'm getting more product terms, which combination is taking the less number of product terms, so that will be selected here. Okay, so inputs will be like A, B, C. So what we have to do here is, so in this product term, if there is a value, then put it as 1. If there is if it is in the complement form, then put it as 0 there. Okay, if it is if there is no term there, then put it as a dash mark there. So in this case here, so AB, I'll put it as 1 here. Okay, I'll put it as 1 in C here. So C, I'll put it as a dash here. Okay, and AC here, so A, there is no B term, and C is 1. Okay, and BC, so there is no A term here, put it as a dash, and this is 1, and this is 1. Okay, and here all of them are zeros here because all of them are in complement forms, 0, 0, 0. So this is the second step here. Okay, and coming to the outputs here, so output, what we have to identify here is whether they are in the true form or the complement forms. So outputs are F1, F2, F3. So I have to mention that whether it is a true form or the complement form. Outputs. So the outputs here, F1. So bracket mention them as a true form or the complement form. So it is a complement form. So F2, so mention it as a true form. And F3, so mention it as a true form. Okay, and so what I have to do here is, so if this product terms are there in the true form, F1 lo me product term unda. Okay, unte 1 bettandi, lekunte dash in bettandi. Okay, so F1, in F1, so I have AB, so I'll put it as 1 here. In F2, I have AB, I'll put it as 1. Okay, in F3, I have no AB here, so I'll put it as a dash here. Okay, and coming to the next one, AC. So AC is there in F1. In F2, there is AC here. Okay, in F3 also there is AC. Okay, and coming to BC here, so we have BC value in F1, and we don't have BC in F2. We have BC in F3 here. Okay, and A bar, B bar, C bar. So we don't have this A bar, B bar, C bar in the first one. We have A bar, B bar in this one. Okay, so 1 and 1 here. Clear?
Yes, sir.
Okay, so this is how we have to design this PLA programming table. Okay, so this is a step we have to use this PLA programming table. So how to design a PLA programming table? First of all, identify the true forms and the complement forms. Okay, so then identify the product terms. So many number of product terms here, number of the product terms, and inputs. Okay, so A, B, C. So whether that input is there in the product term, so put it as a 1. If it is in normal form, it is 1 here. If it is complement form, put it as 0. If there is no term there, put it as a dash there. So coming to the outputs here, so you have to mention them whether it is in the complement form or true forms here. Okay, so afterwards, so put a 1 if the product term is in that specific output here, so put it as a 1. If the product term is not there, put it as a dash there. Okay, so this is how to design a PLA programming table. So next class, what we'll see here is we'll see how to draw the diagram. Okay, so we'll see how to draw the diagram. So all of the people are in mute. So what he'll do here is just on your mics and your videos. So because I think many people are, yeah, so I have problem with this second year people. So we got complaints. See whether you people are just listening or we want to take it seriously right now. Right, so on your videos also, not audios. I want to see you. Who is Amarnath? Who is Amarnath? Amarnath is not there.
Yes, sir.
Yeah, on your video. So what did you listen? Name in the class?
Sir,
ఏమర్థమైంది క్లాస్ ఏమర్థమైంది చెప్పు.
ROM, sir. Construction of ROM.
రామ్ ఇంకా లాస్ట్
PLA, sir.
పిఎల్ఏ. సో పిఎల్ఏలో ఏం స్టెప్స్ ఉన్నాయి?
బూలియన్ ఫంక్షన్స్ యూస్ చేసుకొని కేమ్యాప్ కన్స్ట్రక్షన్ చేసుకున్నాం సార్.
కేమ్యాప్స్ తర్వాత
PLA ప్రోగ్రామింగ్ టేబుల్ కన్స్ట్రక్ట్ రాసుకున్నాం సార్ నెక్స్ట్.
ఓకే, సో అర్థమైంది అది?
ఎస్ సార్.
ఎస్ ఆర్ నో?
ఎస్ సార్.
నోట్స్ రాసుకున్నావా?
రాసుకున్నాం సార్.
యా, సో లిసన్ టు దిస్ రికార్డింగ్ అండ్ నెక్స్ట్ క్లాస్ వచ్చే లోపల అడుగుతా నేను. సో ఎంతవరకు అర్థమైంది అండ్ యూ హ్యావ్ టు షో దట్. సో వాట్ యు హావ్ రిటన్ అండ్ వాట్ యు హావ్ డన్. రైట్.
ఓకే.
యా, నెక్స్ట్ స్వాతి. Where is Swati?
Sir.
Yeah. చెప్పమ్మా, ఏమర్థమైంది? ఏం విన్నావు, ఏమర్థమైంది, ఏం చెప్పినా ఈరోజు?
నేనేం వినలేదు సార్ క్లాస్.
మరి ఎందుకు వచ్చినావు ఆన్లైన్ క్లాస్? ఎందుకు జాయిన్ అయినావు మరి? లాస్ట్ క్లాసులు విన్నావా? రికార్డింగ్స్ వింటున్నావా?
కొన్ని విన్నాను సార్.
ఏం చేస్తున్నావు? ఎంత పనులు ఉన్నాయా ఇంట్లో?
అవును సార్.
కాలేజ్ మానేసి ఊరికే ఇంకా. సో ఐ వాంట్ యూ టు లిసన్ ఆల్ ద రికార్డింగ్స్ అండ్ నెక్స్ట్ క్లాస్ వచ్చే లోపల నువ్వు పర్ఫెక్ట్ ఉండాలి. నేను అడుగుతా. మాత్రం డెఫినెట్ గా అటెండెన్స్ విల్ నాట్ బి గివెన్. టేక్ ఇట్ సీరియస్లీ. ఊరికే ఆన్లైన్ కి వచ్చి సో వినడం కాదు. ఊరికే మ్యూట్ లో పెట్టేసి వెళ్ళదండి. నెక్స్ట్ శిరీష. శిరీష.
Yes, sir.
యామా, ఏమర్థమైంది, ఏం విన్నావు?
About the construction of Prom, PLA, programming logic array, K-maps రాసేది. నెక్స్ట్ దాంట్లో మళ్ళీ కన్స్ట్రక్షన్ ఆఫ్ PLA వచ్చింది. టోటల్ K-map.
PLA టేబుల్ అర్థమైందా?
Yes, sir.
Okay. So listen to the recording and let me know. Like next class వచ్చే లోపల నెక్స్ట్ క్లాస్ ప్రాబ్లం ఉంటుంది, PLA ప్రాబ్లమ్స్ ఉంటాయి. సో అండ్ architecture, you should be perfect with it. Right?
Okay, sir.
Okay, and